Okay, so this is the final lesson of the semester, so that makes it also the final lesson of the year for chemistry. Today we're going to use the math skill that you learned yesterday, which is calculations involving neutralization reactions, and we are going to apply that to something that we call, or to a lab skill that we're going to call titrations. So, titrations are the lab skill that that a chemist or a chemistry student would do in an effort to collect data that would allow them to do the calculations that you guys did yesterday, the neutralization calculations. In a titration, we always know the molarity of one substance, so we always know like the molarity of one substance, and we don't know the molarity of another substance. And so what we do is we add like base to acid, for example, until they get to a pH of 7, or they're neutral. Okay, and some people might argue that at that point we would have moles of acid being equal to moles of base. And that's actually what we were doing when we were doing those calculations. We were making the moles of acid and the moles of base equal. Even though the values weren't the same, we were making that relationship. So the lab equipment that you're going to use when you do the lab is called a burette. And the burette is a very, very accurate piece of lab equipment that measures volume of fluid or liquids. So in this case, it's so accurate that you have to be able to read to pass the to two places past the decimal. So you're going to be, when you record your data, it's going to be like something like this. Something decimal something like 3.07 milliliters or something like that. You will always, when you're working with the lab, with this piece of lab equipment, you will always take an initial reading, and then you'll take a final reading. And then the difference there is the actual amount of that particular substance that you added. And so in these in these readings, the initial reading will be less than the final reading in terms of a value. Okay. Now, the other thing that's a little bit weird about burettes is that how they're marked or incremented. So 0 milliliters on a burette is at the top, and like in our burettes, 50 milliliters is at the bottom. Whereas a graduated cylinder or a beaker or another measuring device that you've used has always been kind of the opposite. It's always like 0 at the bottom and like 25 milliliters at the top. So what I'm getting at here is that we read the scale going downwards. And for beginning chemistry students who are using a burette for the first time, that's sometimes a hang-up that students struggle with. So what we're going to do is I'm going to skip this slide and I'm going to come back to it. We're going to talk about it later, but I want to take a little bit of time to practice some burette reading as a class here. So in this instance right here, we have the same burette, but it's kind of like chunked into two sections. So we have the initial reading and the final reading here. And so the first thing I want to point out is that the scale on this measuring device goes 12, 13, 14, 15, 16. So it goes down, right? So the scale is going down, which again is something that I've mentioned already. But when I'm looking at the scale, what is each dash or mark equal to? Looking at the scale of the burette up here, what is each dash worth? Yeah, it's worth 0.1. So like this would be like 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. Okay. And when we're reading this burette, the thing that beginning chemistry students sometimes struggle with is they want to say it's like 13.4 something or maybe 13.3 something. In this case, because we're reading from the top down, we are going to say that it's more than 12 but less than 13. So we're going to have something like 12 point, and when I look at my scale, it's more than 12.6 but less than 12.7. So this is going to be 12.6, and then I'm going to make a guess. And to me, that looks like it's somewhere around 0.67. Okay. And then I'm going to use my unit because we don't want to have a naked number like so. Now, I'd like to point out that these green numbers here are known or certain values. Like those are for sure. But this red value here is an estimated digit. Okay. And it's a guess. And the other thing that I would like to point out is that not everybody reads the same measuring device exactly the same. What I mean by that is that I might look at that and say it looks like 12.67 to me. You might look at that and say it's like, I don't know, it looks like 12.65 to you. That doesn't mean that I'm right and you're wrong. It just means that when you're reading the burette and when I'm reading the burette, we always want to do it the same. So every time you read a burette, if you should have an idea as to about where like 0.65 is or 0.75 is, and like always kind of use that as a reference. So the next part of this slide is the final reading portion. So at this point, we have an initial volume right here. Okay, so that's the initial volume that we collected. That's where the burette was at before we added any solution from it to our setup. Now, I'd like you to take a second and read the final reading here on your own. So go ahead and take a second or 15 and actually read this burette. Okay, so hopefully you've recorded your answer to 2 decimal places. The way that I read this burette is it's more than 18 but less than 19, so it's going to be 18. And it looks like it's more than 18.4, but less than 18.5 because this would be like 0.4 and this would be like 0.5. So it's going to definitely be like 18.4. And then my estimated digit or my best guess digit here, I think it looks like 4.8 milliliters personally. But again, as long as you are reading the burette the same way, you should be okay. And as long as it's within reason, you should be okay. So this is going to be our final volume. And the reason why I'm bringing this up or speaking about it in terms of like initial volume and final volume is because you might recall that when we did heat calculations, we had a change in temperature, right? And that change in temperature was like final minus initial. And this is not actually any different. So change in volume here is going to be V final minus V initial. And so in this example here, I'm going to take the 18.48 milliliters minus the 12.67 milliliters. Okay. And when I plug that into my calculator, I get something like a change in volume of 5.81 milliliters. Now, some beginning chemistry students run into the trap of like, I'm just going to round it to 5.8, or I'm just going to round it to 6 because it doesn't matter. But the reality is that when you're reading something off of your burette, your volume must have 2 decimal places. Yeesh. Kind of ran out of room there. Must have 2 decimal places. I hate that, but you get the idea. Must have 2 decimal places. Man, I can do better. I can do better. There you go. Okay. So just make sure that you're recording your volumes to 2 decimal places when we go into lab on Monday. All right. So let's look at an example of what math you're going to do when you collect your data on Monday. Actually, yeah, let's do that first. Okay, so before we go any further, how do you remember, or how do you tell if you have an acid or a base based on its chemical formula in this class? So the question that I'm asking is, which of the chemical formulas is a base in this example? The KOH, right? KOH is a base because hydroxide is present, meaning the HCl is an acid because it leads with a hydrogen. So in reality, we know a couple of things here. We know the molarity of the base in our data table because it's given to us in a problem. And we also know the initial volume of the base, so where the burette started at, and we know the final volume of the base, where the burette ended at. We also were given the initial volume of the acid and the final volume of the acid. And what we don't actually know is the molarity of the acid. Okay, so that's something we don't actually know. So we're going to be solving for molarity of the acid at some point. Now let's go back up to that diagram just a second here. So in this situation here, we are going to probably, or actually when we're in lab, we're going to probably have base in the burette, and we're going to probably have acid in the Erlenmeyer flask. What we are also going to know, or not know rather, is we are not going to know the concentration of the acid. So it's going to be an acid of unknown concentration. And I'm going to put big M in parentheses because molarity means concentration. We are going to have a base of a known concentration. And I'm going to put molarity in parentheses there. Okay. So we're going to add base to acid until we get to a pH of 7 or as close as we can. And that's basic, and that's how a titration works. And we'll have plenty of practice with that on Monday. So let's go down to this problem here. This problem here has a lot of information in it, and I'm going to break it down into 4 steps. Okay. So the first thing that I need to know is the actual volume of acid and the actual volume of base that were used. So in this problem, the first thing that I need to do is calculate the volume of acid and base used. So for the acid, I'm simply going to take the final, which is 10.97 milliliters, minus the initial, actually, let me do it this way, minus the initial, which is 1.56 milliliters. And when I plug that into my calculator, I get something like 9.41 milliliters. Okay. For my base, and I'm being purposeful with skipping a little bit of space here, I'm going to take my final, which is 39.52 milliliters, minus my initial, which is 23.65 milliliters. And when I plug that into my calculator, I'm going to get something like 15.87 milliliters. Now, something that's important to think about before we get much further is at some point we're going to be using the molarity formula. And just to refresh our memory, the molarity formula is moles divided by liters, right? And if it's moles divided by liters, before I go any further, the volumes that I just calculated, can I use them as they are, or do I have to do something to them? Look at the units of the volume that I just calculated and compare it to the unit of the volume needed for molarity. So I'm just going to plug 15.87 into the molarity formula. Right. So I can't just use it as it is. I have to convert it to liters first. So I'm going to do that for both the acid and the base. And so when I do that, it's going to be 15.87 milliliters times 1 liter over 1,000 milliliters, which will give me 0.01587 liters. And I'm going to do the same thing for my acid. So I'm going to take the 9.41 milliliters times 1 liter over 1,000 milliliters, and I'm going to get 0.00941 liters. Okay, so that's the first step. The second step here is I'm going to use the given information that I have, which in this case is I know the volume of my base and I've been told the concentration of my base or the molarity of my base. So that tells me that I'm going to calculate moles of base used. So the second step is to calculate moles of base used. And to do that, we are going to use the molarity formula. So that's molarity and moles and volume, in this case, liters. We know the number of liters because we just calculated it right here. So I have the 0.01587 liters. We were given the concentration of the base here in our data, so it's 0.121 molar. So we're going to solve for moles. So in this problem, I'm going to take molarity. I'm going to use the molarity is equal to moles over liters. And I know that I have a molarity of 0.121 molar. And that equals, in this case, we're solving for moles. So my volume is going to be 0.01587 liters. The next step is I'm going to solve for moles by multiplying both sides by the volume. So that's going to be 0.01587 liters times 0.121 molar. And that's going to, when we set that equal to moles, so when I plug that into my calculator gives me a value of 0.00192027 moles of my base, which in this case is KOH. The next thing that we have to do, just like we did yesterday we found the moles of the base used, or the moles of the acid, whatever our starting point was. The second step here is we are going to be doing a mole conversion, right? So we are going to go for step 3 here is convert moles of base to moles of acid. And for us, that's going to be a stoichiometry problem. Yes? Sure. So in this case, I'm going to take the number of moles I just calculated, which is 0.00192 moles of KOH. I'm going to put it over 1. And when we go mole to mole in a stoichiometry problem, what do we need to know, find, or calculate? Or what do we need to use? We need to use the mole ratio. So in this case, we have our acid up here in our balanced chemical equation, and we have our base up here in our balanced chemical equation. So if I was going to identify my mole ratio, I would say that it is 1 mole, it's 1 mole of acid, in this case HCl, for every 1 mole of base, in this case KOH. So when I go to fill this in to my equation, right, I'm going to set this up so moles of KOH cancel out. So I'm going to put 1 mole of KOH on the bottom, and I'm going to put 1 mole of my acid, in this case HCl, on the top. And hopefully it should not come as a surprise to you, because when you multiply across and then across the top and the bottom and then divide, that in this case you're going to end up with literally the same answer. It's just going to be HCl. So you're going to have something like 0.00192027 moles of HCl. Our last step here is to calculate the molarity of the acid. And we know the acid in this case is HCl. So I'm going to identify my variables. So molarity, we don't know. Moles, we just calculated. And the volume, right, this time I'm going to use the volume from my original calculation, which is 0.00941 liters. So I have my molarity formula, which equals moles over liters. So if I just plug in what I know, in this case, it's going to be 0.00192027 moles over 0.00941 liters. I would grab my calculator and plug that into my calculator. And my final answer here for the molarity of my acid is going to be 0.204 molar HCl. And I know that this looks like a lot, but again, remember that when I teach these things, I try to show all of the steps. And when you're doing this in class or when you're doing this for homework or you're doing this in a lab, you don't necessarily have to write all the things out. You just have to do the steps. So it's not as bad as it looks, I don't think. But if you have any questions, definitely don't hesitate to ask. These are the calculations that you will be doing on Tuesday, actually after you collect your data on Monday. So yeah, that's that. And that is the final lesson of the year.